universe, so they have to be medium scales. Basically said a small fraction up, so the communication time between the galaxies is small, that are expanding is small, so that we don't have the problem that gravity doesn't really, at least in general relativity, doesn't travel at infinite speed, but at the speed of light. But if they're close together, it's, you know, you can consider it infinite speed. Like, I mean, I see you like a nanosecond or something before the time. There is a time delay between the time I see you and the time light emitted from you, but it's a nanosecond, so it doesn't matter, so you can consider the speed of light infinite. You're not light years away, you're a nanosecond. Okay, so something like that, close to this. And we said that we can take this medium-sized sphere, big enough so that the universe appears homogeneous, small enough so that speed can be considered infinite, and we calculate the mass outside doesn't contribute, and by Gaussian, the mass inside is Gm total, the force inside, the force at the surface of our sphere, expanding sphere, is the mass inside over the radius of the sphere squared. So that's what we said. And we said that this is an equation like that of an expanding ball. This is not working. Okay, so this equation of an expanding ball is like a ball thrown up vertically. Vertically like that. Because a ball thrown from the Earth vertically, also the mass of the Earth is obviously conserved, and you have a vertical coordinate. So this is perfect vertical, so this is just a draw. This is perfect vertical. One coordinate r, no theta pi's or things like that. Okay? And a ball can go and just escape, or come back to the ground and so on, and this is determined by the energy. Negative energy ball comes down, total energy, which is the constant of motion. This is by integrating this equation here, you should convince yourself that d by dr of d r by dt is squared. Half of it is equal to this, so that you can integrate this equation. This is trivial, this goes to r, and this will be dr by dt squared. Okay, so this is your energy integral. In Hamiltonian mechanics, when you have an energy integral, you have one integral, 1 degree of freedom. You can solve the equations, and this has explicit solution. Okay? So, okay, and we said this was possible because the expansion was scale-free and so on, and we heuristically said there's a dynamic of time that is 1 over square root of 0, and that makes the solution scale-free. Actually, that's not that completely accurate. This is accurate to some extent, but it's accurate exactly only when E equals 0. If E is not equal to 0, there is another parameter, a constant, but it's a constant for all Newtonian expanding spheres. Okay? So therefore, it's again scale-free or self-similar solutions. So how do we do these self-similar solutions? You do it by, usually, when you suspect there's a self-similarity, you multiply variables. You multiply your radius, your Newtonian radius that we had of the Newtonian sphere, by some scaling, okay, and a function of time, a function of space and a function of time. So this radius is scale-free in the sense that you can separate it into only a space and only a time function. Okay, and you put this substitution here into your equation, and you get something really interesting. There's a constant 2e over some r squared, that this is rs, but because it's a fundamental constant of the universe, as we will see later, we'll just do it as r here. That is constant for all these spheres. the Newtonian integral motion over of the particle, of the sphere, over its radius squared. This is 1 over time squared, its dimension. There is a 1 over time squared constant for all the spheres E of t, independent of what r is. Okay? So what is it? We don't know. How did we do this? We just did it for normal matter. We just did for n is 4 pi over r cubed time rho. Okay? You get this equation. Let me put this in. Okay? Is this clear? It's quite clear.
Can you explain again why we wrote R as R?
Because we want to get a similarity solution. We want to get that all spheres have a common solution. We are suspecting there is a similarity solution.
What do you mean by similarity?
Similarity is this. This is a similarity solution. That all the spheres, independent of their RS, have the same constant. It's not obvious that they have the same constant, is it? Not all things in the universe, it could be that the spheres are expanding differently. They're not. That's what we want to show. A of t is the same for all the spheres.
Okay.
Self-similar. This is called a self-similar. It's not always like that. We have intuition. You know, we are suspecting that this is the case, and we want to try to find what's really deep about it. Not yet.
But this second equation it includes R in it.
Yes, but this is a constant. The 2e over r is a constant. R squared is a constant for all spheres, independent of the e and the r. It's a fundamental thing about our universe, but we don't know what it is. Okay, so that's the thing. When we put that, we suspect there's a self-similarity solution because of that. We see that this thing is making a problem. It's self-similar when this is 0. It's obvious completely. We can try it. It's out. Okay? 1 over square root of 0. Okay? Because there's no scales, whatever, other than the density, you know? But this energy here puts a scale. So we're trying to take it out and make it constant. Okay? This is called a similarity or scale-free solution. Huh? They're very important in physics, generally, by the way. For instance, like you can get power laws are very important in physics, and blast waves. Okay? Keep it around. And why it is so is really because of the 1 over r squared problem, the power law. Okay? This is not obvious. This, we are suspecting that this could be the case. This tells you the expansion is the same for any sphere. It doesn't depend on the sphere we chose. This is important. Otherwise, you cannot do any Newtonian thing or some similarity. If all the spheres expanding differently and the universe is homogeneous, they'll start getting different density. Start getting into each other and you'll start getting inhomogeneity.
I mean, why would I expect that different spheres might expand differently? Is it the same Newtonian law?
Exactly, so we want to write it down.
Yeah.
We want to write it down. We want to do, we want to write it down so that we can compare with observations and so on. We cannot just say that and go home. We need to, work it out. Otherwise, no. So, but we cannot know this fundamental constant a priori here because we are Newtonian. We are limited to our small patch. This may be a global thing about universe for all we know. We are limited to a small Newtonian patch. How small? It's this. It's within something called the Hubble sphere. Okay? That's the limitation of our Newtonian analysis. Okay? Formally, or semi-formally. Okay? A Hubble time, you can define something a Hubble time. It's the time for the universe to double its size. Okay? A dot times the Hubble time is A. So after a Hubble time, it's 2A. If it was A, it will become 2A. And you write it like that. It's A dot over A is the inverse of the Hubble time. Or A over A dot. A dot over A is the Hubble constant, which Hubble parameter, which is the inverse of. For normal universal, meaning those not inflating exponentially. We'll talk about that later. When the expansion is like that, about the 2 Bayani for the rock universes we've been talking about, or let's say Newtonian universes we've been talking about, they can expand and recollapse and so on. And the Hubble time is just a linear extrapolation, which is similar to the age of the universe. So therefore, if we put a current Hubble parameter of 71 kilometers per second per megaparsec, try to do this in second -1 and see how it works. You'll find that it's about 14 gigayears. Already you can know the age of the universe from measuring this Hubble parameter. Now, how do you measure it? We'll get to it later, next lecture. I'm just saying this. So the Hubble sphere then is the sphere, the light travels in a Hubble time. Okay? The sphere that the light travels in a Hubble time is called the Hubble sphere. And this basically is this, you need for your Newtonian analysis to work to be within the Hubble sphere, well within the Hubble sphere. You don't want the expansion time of the universe to be faster than your communication time with galaxies. Otherwise the universe would be expanding and galaxies are not communicating well, and the Newtonian approximation breaks down. So, you know, Newtonian approximation is valid within the Hubble sphere so that galaxies can communicate with the speed of light much faster than the dynamics itself changes. So the dynamics is really effectively that of an infinite speed of light. Done? Now, but there are other things you need to add to our Newtonian thing other than going beyond the Hubble radius of the Hubble sphere. We need to add things that are fundamentally relativistic. Even within the Hubble sphere, things can be relativistic. Photons are always relativistic, no matter what the expansion speed is, and no matter what the communication time is. Photons cannot be treated in a Newtonian manner. And any particle that is relativistic will be the same. So neutrinos, if they are relativistic, or whatever else. Okay. So who knows the Poisson equation? Gauss law. Last time we talked about Gauss law. This is the differential form of Gauss law. Okay. So the differential form of Gauss law, as always for gravity, you have G instead of the epsilon naught. Okay. But this is gravity. So this is the Newtonian equation that GR should, general relativity should, as a gravity theory, should tend to. We want to modify this heuristically so that to include things like radiation and anything else that is similar, that is similarly fundamentally relativistic. So you know even from special relativity that momentum will contribute to the things moving, contribute to the energy. Okay? And there's an equivalence between the mass and the energy and the momenta and so on. So we need to include such things. That's the first observation. So momentum should contribute to gravity, not only the mass or the effective mass equivalent of the energy. Energy equivalent of the mass. Okay? And also, we see this rho doesn't transform like a scalar under a Lorentz transformation. It's not a scalar. It changes from coordinate to coordinate. Rho is n over r cubed. And it doesn't, so therefore it transforms as a Lorentz factor, 1 over the square root of 1 minus v squared or c squared. Transforms like, not like a vector. A vector would have 1 gamma. An element of a 4 vector would have 1 gamma. A scalar would have no gammas. It's like a tensor. It's a gamma squared. Okay, so it's a component of some tensor. What could it be? It could be, it has to be something made of momenta if we're gonna recover some of the special relativity. Well, how do we do this? So we want to do a tensor made of momenta and energy. So an energy momentum tensor, because we think this thing is a component of the tensor, we want to find other components of the tensor. A matrix for the purposes here. Okay, we know already from classical hydrodynamics, normal, Newtonian Newtonian hydrodynamics, that we have the stress tensor of 9 components. What is the stress tensor of 9 components? If you have like fluxes, okay, it's composed of fluxes. Good, Alexei, erase that one too. Okay. So if you have fluxes, if you have you will see this a lot in statistical mechanics, tubes like this. We start to change these things, by the way. Okay, so a number density of particles n over v, moving at of mass m moving at velocity v. This is the flux per unit time. Are you convinced of that? Mass flux per unit time, rho v. Okay. Momentum flux is rho v squared. If all are moving with the same speed v in this direction. So this is mass flux, momentum density. This is momentum flux, rho v squared. Okay. Is that clear? If it's not isotropic, meaning the momentum could be this like that, a vector, and then you have j here over I, then it would be vi vj, rho. Let's go to that. Rho vi vj. Is that also clear?
Hey, are we taking the magnitude of the momentum?
Yeah, and projecting it and so on.
So we're not worrying about momentum in different directions?
No, it's in different. I mean, this is like a component of J on the surface I.
I see.
Okay, it's anisotropic. Okay, and then if you have a distribution, you take averages Vi, Vj. Okay, you take averages. So this is how you get a classical stress tensor in hydrodynamics. There's no relativity. Okay, in relativity, you'll have an extra component. You have 4 velocities, which you can put as 1 here, so that we have this remaining like a Poisson equation, not rho c squared. We have rho, and there will also be g mu, but I'll leave that. Okay, if we have a chance. Okay, so this is these are the components: energy density, the one in the Poisson equation. These are energy fluxes, or equivalent momentum density. In general relativity, at least these are equal. Okay. So this is equal to that. And then you have the anisotropic stresses, the Vij, these guys. And then you have the isotropic stress, which is the pressures. Okay, there are 3 pressures. Vxx squared, Vyy squared, and Vzz. Okay, is that clear? This is the stress tensor, energy momentum tensor. Now we're gonna, this thing reduces really nicely in these maximally symmetric spaces, meaning isotropic and homogeneous. So there's no streaming. There's no reverse streaming because it's isotropic by symmetry. And there's no cross terms, so the Vij go. Otherwise you would have viscosity and anisotropy and so on, and you wouldn't have homogeneity. And so it's a perfect fluid, no streaming. No streaming is no average motions. Perfect fluid is no anisotropic stresses. Okay? You're left really with the 3 pressures and the energy, which in our Newtonian limit, you can add them up like that. Meaning the small patch quasi-static, okay? That, communication speed, speed of light, and the stuff we talked about. Communication speed smaller than the expansion, communication time smaller than the expansion time. Okay, so you have your Poisson equation plus the 3 pressures, Vxx squared, Vyy squared, Vzz squared, and so on, over c squared, okay? Because we're dividing that by c squared. So this is our new, sometimes these call it a Friedmann equations. I like to call it an acceleration equation. Some people call it the first 3. So this is a new Friedmann equation or a new acceleration equation, similar to the tuba, similar to the ball or the rocks thrown up, but now, first of all, scale free, with A double dot instead R double dot, which we'll forget about for now, and with the pressure term for things that have pressure, relativistic pressure. So we need to look, these are not hydrodynamic forces in the Friedman or acceleration equation. Hydrodynamic pressure has a force when nabla P is something. We can't have here any nabla P's, okay? Because if we have nabla P's, we have gradients of pressure, we lose our homogeneity. Okay, so we don't have that. So what is this pressure? It comes from its mass equivalence. So if it's positive, it's attractive. It's like an additional mass. It's as if you put, it's negative, it's actually repulsive. Huh? And it's only for relativistic things because it comes like that, rho v squared over c squared. So if v is small to c against rho, this is very small compared to that. So it's only for relativistic things. It's not for normal matter, where v over c is small. Okay, so this is the important bits about the pressure. So this is only. So for example, for radiation, P is a third rho c squared. You can do this from Carnot cycles and so on. If you did thermodynamics, you can look it up. For radiation, the radiation pressure, there's a radiation. If you didn't do it, by the way, look it up because we'll need it to when we discuss the cosmic microwave. So read out radiation pressure on Wikipedia or something like that. Okay? So it's a third. So this will be a third for radiation pressure. There's other things that are much more exotic than that.
So
Yes.
how much of this derivation so far are we supposed to be following in detail, and how much of it is just standard material from fluid dynamics? Because
No,
I
this
don't
is,
think I can read this.
You can read the stress tensor. No, this is standard material from fluid
Standard
dynamics.
material,
Yeah,
yes.
you want to know. There's nothing that we are at. This is actually from Wikipedia, this picture. This is not very exotic stuff. Yeah. This picture is, I say.
But I'm not expected to reproduce this. I'm not expected to know how to reproduce it from first.
Well, it's quite trivial actually. You look up any book on fluid dynamics. This part is in any book on fluid dynamics, and this part is any book on general relativity. If you want to repeat, it's not trivial. You can repeat. It's not. I mean, it's not difficult. It's fairly straightforward. Okay. So. This step here is a bit heuristic. You know, this is not actually nobody does it really.
So it's perfect fluid. Let's just
Yeah. No, it has to be a perfect fluid. By symmetry, you know. I mean, no. This is fairly. It's like that in lab book.
Yeah.
In any lab book on hydrodynamics, if you have isotropy and homogeneity, it would be a perfect fluid.
Yes.
There's nothing exotic about it. This is basic physics. You know? So there's nothing really. People think because it's cosmology. No, that's the point. It's really, basic intuitive stuff that you can find. I mean, this thing is people in material science use it. And they're negative pressure. I mean, engineers next door use it. You know, this stuff is tested on tested on vehicles making accidents, and in solids. It's also applicable to solids, but in some a bit modified form. It's applicable to the people doing renewable energies, things that are, this one. But the relativity part is also well known. It's not a big deal. This is really, there's nothing really amazing about that. I mean, I don't want to take too much time, but I got really disappointed when I first arrived to Sussex in 1993, 30 years ago, and that I thought there were so things that are really deep. It's not, science isn't, in my opinion.
Good.
It's for very simple stuff, made sophisticated by by digging into it. That's my opinion of things. Okay. So that, for example, what makes you understand that even though we use very normal hydrodynamics, this is not hydrodynamic pressure in the normal Newtonian pressure from movement with a gas in a gas canister. But making a pressure, this is nothing like that. This is a universe could be infinite and homogeneous and have this pressure force without any gradient. In a normal Euler equation, you need gradient. So this is what's important bit in relativity. This is what's new. relativistically, cosmologically speaking, this pressure is a mass equivalent. It's a relativistic. So this is not trivial, really, at this. But the other stuff is trivial. This stuff is in any introductory kinetic theory book you'll find it in. You'll find it in life and in anything, you know. Okay? And you'll find this too, the first law of thermodynamics. If you want to be highbrow, this is equivalent to the divergence of the energy momentum tensor being zero. But because we are here in a very simple system, it reduces to just a third law of thermodynamics, the first law of thermodynamics. So why do we need a first law of thermodynamics? Because we, when we did the cunning thing of doing a Friedmann equation from the acceleration equation here, we just assume that m is 4 over 3 pi r cubed, rho. Okay, but this is not the case if you have this pressure. And we have a pressure term now in our new equation. What do we do with it? We need an energy equation, energy integral, but we have a pressure here that we don't know what to do with. Now, physically speaking, what does it mean? It means if you have normal matter and you expand it, the density, the energy density or the mass density, which is equivalent for normal matter, is goes 1 over the volume, 1 over a cubed, you know, if this is, but that's not the case for radiation, for example. Radiation, the number of photons goes down over 1 over a cubed, but each photon gets redshifted. H mu becomes mu goes down, so it's 1 over a to the 4, actually. So you need to take that into account in this equation. You can't just put a cube like we did. Okay? So the internal energy is this. Okay, the relativistic internal energy is this. We want, if P equals 0, then this is rho V is constant. 1 over a cubed. But P is not 0, then you get different things. P equals 0, this is just rho V equals constant. Yeah? Rho V equals constant, meaning rho is 1 over V, just like our regular equation. Like the equation of
this is not entirely
matter. Huh?
If P equals 0, we will have conservation.
No, you always have conservation, but you'll have conservation of the mass
I see.
and the energy density.
I see.
Okay?
Yes.
Without the pressure.
Yes.
Okay?
Yes.
The other, if you have radiation, you still have conservation, but each photon is losing.
But redshift is not conservation. Redshift is mysterious loss.
No, it's not.
It's not?
It changes the expansion of the universe.
Okay.
You will see.
Okay.
No, it's not. In these simple things, and you can do energy conservation pretty well. That's why you could do in Newtonian. But that's not in general. In general relativity, energy conservation is not. Okay, as I but in this case, it's fairly straightforward. Okay, so we put that here. This becomes a total differential. Can you see that? This is a total differential. Rho a squared is this is like d rho a squared. Right? You multiply this by a here, and then do d differential of rho a squared, you will get this thing. Okay? So therefore you can integrate this and get our constant again. Okay? So this is the energy integral including pressure. This is the Friedmann equation again with the constant. But we don't know what it is. To know what it is, you need a bit more general relativity. You need to have a metric. Okay. So now the metric is again easy, relatively speaking, because you need a metric because you need a metric tensor really to do general relativity, as we'll have one slide quickly about it. We have a metric tensor, so from it we have a metric. Okay. By symmetry again, you can decompose your metric into space slices and time slices. There is a careful discussion on a book by Peebles, Physical Cosmology, on this, if you want. A heuristic discussion is as follows. You can have your Newtonian absolute time again. That's why we could do Newtonian. That's another reason we could. You could have your Newtonian absolute time again, more or less, at least, to simplify things. You could have other times and other coordinates and so on, of course. But you can simplify things by having an absolute time. Why can you have an absolute proper time? Because of the constant density as a function of time, observers can agree on the time by measuring their density, or more precisely from the temperature of the cosmic microwave background, which we'll discuss next week, for example. So if I'm here and I measure 3 degrees Kelvin and somebody there measures the same, or I measure some density and somebody measures the same, we can synchronize our clocks this way. Okay, so you can separate the time component and a space component. They can be entangled in general, okay, in general relativity. But here we can separate it into a time component, and I do a minus. You can do the reverse. It doesn't matter in the end if you change also the energy momentum tensor. But anyway, but this is like the Minkowski in the standard form. Okay. So this is the time component and the space component containing the scale factor. Now, if dl squared is just dx squared, dy squared, and dz squared, and a is 1, this is just a Minkowski metric, flat. Okay, so there are two curvatures here, so to speak. One connected with the time evolution, roughly speaking, this is the rough, and the other connected to what this thing could be. Okay, the dl squared. It may not be flat. May not be simply the Euclidean. It could be something else. So it's not Minkowski. You can define a proper distance similar to a Euclidean distance, but now with the A and with the L that may not be flat. Okay? So what is this L, first of all? You can have spatially curved surfaces. So let's do a 4-dimensional space. Now we're doing only the space part, huh? The dl. We forget about the dt for the time. We do only the space part. So let's do a 4-dimensional space. We set x, y, and z. We have an additional coordinate w. A polar coordinate system in this space, we add an extra angle chi. Okay, so if you take this chi off, then you end up with normal polar coordinates. This is 0, say, right? Or 90. 90. So this is 0, and this is 90 degrees. Pi over 2. And this is 1, and you get back your x, y, and z. You do an extra coordinate here, and this is the definition of a sphere. A normal sphere is that, a sphere embedded in a 4-dimensional space is this. Okay? So this is for a positive curved space. What we're trying to do is get the metric for a positively curved space, the space one, okay? Which we have already isolated from the time point. Okay. Then this is you can do this as a very simple exercise. You can take the derivative of dl, okay, which is dx squared, dy squared, dz squared from these things, and you get this thing. You can do this exercise, it's really easy. And you can do it for negatively curved where the sine becomes shine and so on, hyperbolics. Okay?
What did we need for the first place to choose a 4-dimensional spherical coordinate?
This is standard way people are doing that. You can embed it in local coordinates. You can embed it on coordinates, but it becomes much more complicated. It's much easier. This is the convention, so it's much easier. And also, it's much easier from the mathematical point of view. It's also to connect it to Euclidean distances and so on that you want to measure in cosmology.
أنا بس still مش شايفة إيه الفرق ما بين إن أنا أعمل كده. يعني I could have chosen a 3-dimensional spherical coordinates خلاص. يعني how would this make
but that would be 3-dimensional. No, you can't have no. You can't have normal spherical coordinates on a sphere. No. You need to embed it. This would be a 3-sphere, not a 4-sphere. It would be a 2-sphere, I mean. This is a 3-sphere. This is a 3-dimensional sphere. What you're talking about is 2-sphere embedded in 3. No, this is different. Okay, this is a 3-sphere embedded in 4. You don't have to embed it. You can do it without embedding, but it becomes really complicated. Okay. Right, so this is our metric, space part of the metric. So the space part is 3-dimensional. There's 4 times. Okay? So this is the metric. You can also write it in a different way that will be quite useful when we measure distances, luminosity and angular diameter distance, because you have something like Euclidean coordinate r. It's not really Euclidean unless this thing is 0. If this k is 0, so what did we do? We wrote some new coordinate, r equals r sine chi, okay? And we just substituted this thing in there, and you can also go through this, and this you can do. I'll give you a PowerPoint, and it's useful for you guys to do the exercise.
Is this FLW?
Huh?
Is this
Yes, but not yet because we're missing the time point and the A. But next slide, it will be there for W. It's almost there. If k equals 0, this is just a Euclidean coordinate, the r of the Newtonian. But this r is not always the r of the Newtonian sphere. It's only r of the Newtonian sphere when k equals 0. So what is k? It's 1 over r squared. It's a curvature. Okay? So k is a radius of 1 over radius of curvature squared. So it has the dimension of a curve, of a scalar curvature. Okay? It has that. So this k. So what is this geometry? And you can also write it like that, with a sort of angle multiplying r squared. So this gives you an area, and this gives you squared of an arc length. Okay. So what is this arc length? It's a geodesic distance. Okay. On the sphere. Now this is really a three-sphere, but we can draw it. So it's a two-sphere. So this is the geodesic distance. This r is the Euclidean projection. So the Euclidean projection is equal to the geodesic distance if this is 0. Otherwise, it's not. Okay. So this is important for measuring the curvature of the universe, but we're not there yet. This is a long way. Okay. And this is your angle chi and theta and phi. So this is an arc distance. Geodesic distance, r theta is an arc distance on the sphere. And this is an area element, and which contains the square of a theta circle, an arc of a theta circle, and the phi that we can't see here because it's on the third dimension. Okay, you can't see. There's a phi also. So this is an area element. This is a circle, and so on. This is our basic geometry. Sorry.
the previous one.
Yes.
معلش هو الار كاي اللي هي الجيوديسيك ديستانس دي موجوده فين بس على الرسمه؟
This.
that part.
This thing. This. So if
How
I
is
am
that different than من الارك length على السبسفير؟
yes, because this is actually this is not. No, this is not the same because this is not a big circle.
Oh, okay.
This is a big circle. Geodesics are big circles.
Okay.
Okay. They need to pass by the poles. Okay, so here's the FRW. The FRW. It is the RDL squared multiplied by A squared, and we put the time minus C squared dt squared in this signature. So, and this is the FRW in the other coordinates that we started with. Now, these things can be changed. There are different conventions, so these are not really absolute values, you know. It depends on how you define them. For example, some people define K like I did, which I will use for all purposes later, as 1 over r squared minus if it's negative, 0 if it's flat, radius of curvature goes to infinity really, and 1 over positive 1 over r squared if it's positive. Now you can only have constant curvature because again homogeneity and so on. So you cannot have curvature vary. So the three cases that we can have is flat spatially. It's never flat on the time because there's dynamics. We'll get to that briefly. So flat spatially or negative or positive curvature constant. You can't have anything else. So some people also like to, in that case, A is dimensionless, and A usually taken to be 1 nowadays. It's a scale factor. Because we didn't care about what everything is expanding the same way. So we really don't care about the value. We will care about other things. There are other things, okay? So some other people like Q to be minus 1, 0, and 1. Okay? Signature. Positive curvature, 1, negative, minus 1, and 0 is 0. and they take R to be equal 1. In that case, A has a dimension of length, because you need length somewhere in this thing. So A is in meter or kiloparsec or gigaparsec or whatever you like. And you have the three cases. The positive curvature, I'll get to this all in a later. Take this positive curvature, you are on the surface of a sphere like this one. Negative curvature on a sort of hyperbolic surface, but 3 hyperbolic, and flat where the triangle makes 180 degrees like Euclid thought it should. Sure. So, this, the title will go off, but it's not a big deal, I guess. I don't know why it's doing that. Because this thing is okay. So what? GR in one slide. Okay. So how do we want to just get a feel intuitively how this stuff can come out from general relativity? Maybe Dr. Adel and also Dr. Walid and so on will discuss more how that works out. But let's try to get an intuitive physicist, very naive physicist feel of how these things. We needed a metric tensor. These are metric tensors. It's the diagonal -1 for this thing, for the light, and this thing for the r coordinate, and this thing for the theta, multiplying the theta coordinate, and this thing multiplying the phi coordinate. Okay? So 3 coordinates because it's 3 sphere. Okay? So, and the fourth is the time. Okay? C squared, dt squared. So this is it's diagonal. It has to be because the energy momentum tensor is diagonal. It was rho, p, p, p. So this has to be the same. It can't be anything else, and because of the symmetry. So these are the Einstein equations, which Dr. Adel, I guess, will provide for you. So what are they? For our purposes, they contain the energy momentum tensor, which we already saw on one side, and the other side, basically the metric and many very complicated derivatives of the metric. Okay, for my purposes, this is it. The metric and derivatives of the metric. On one side, so here we got everything really in principle. But to actually get the Friedman equation, you'll need a few pages of calculation. But you can also do it and cheat with Walid Hanafi and the GR tensor. Or you can just intuitively bypass it with me. so 3 different ways of doing it. Intuitively bypasses, this is just derivatives of the metric, and this is just the thing. So we have the metric, and we know how to solve this in principle. We'll get also 2 equations, really. One for the density. So this is called the Ricci tensor, which contains all sorts of things, derivative, something called the connection, and derivatives, or whatever. And you had 2 components, a rho, which was T00, and the T1 ij 1 to 3, which were the pressures. So we intuitively will have components like that also for the geometry. So the 0, 0 is really the time. The 0, 0 is really the time derivative. So what we had, a double dot in the time derivative in the Newtonian comes here as a curvature in the time, in the time curvature. Now, this static meaning I do the Rij components 1 to 3, 1, 1, 1, 2, 1, 3, 3, 1, and so on, of the there will be 1, 1, and 1, 2, 2, and 3, 3 because they're isotropic. Static means I'm taking here the time derivative 0 to show you where the spatial curvature comes, because there's other time components in this thing, but I'm taking the space one. I'm just doing a static for the Rij, okay, to show where the curvature comes. It comes from the space one. And here we go. It turns out this is our constant. Our E over R squared of the Newtonian is really the time connected to the time the light takes to do the radius of curvature of the universe. Okay? because this is it. This is 1 over r squared times a squared. This is the radius of curvature of the universe, and this is c squared. So this is the squared, inverse squared of the time the light takes to cross the radius of curvature of a curved universe. We could not have learned that only from the Newtonian, okay? So from our purposes, this is what we're learning from the GR. The Newtonian thing turns out to be connected to the curvature. It's a global, say, well, at least it's a property beyond the Newtonian small patch approximation. Okay? Because of the Newtonian small patch approximation, you won't see any curvature anyway, even if there was curvature in the Newtonian, because it's a small patch. Okay, so this is the radius of it. This we said 1 over time squared. So this is 1 of the time squared of the radius of the light time takes curvature of the universe. Okay, so it has a dimension of it's connected to the Ricci scalar. This is the Ricci scalar of space, not space-time. Ricci scalar of the space. So it's connected to the Ricci scalar, as we may have expected from here. Ricci scalar is the sum of the Ricci tensor. Basically, you take this thing and sum it Gij and take Ij top, you know?
Yeah. So.
And you sum it up, Gij, you sum it up, you get 3, because there's 3-dimensional space. So 3 times 2 is 6. Okay?
Why are we saying of space?
This is the lower one
Why are we
of the
saying,
metric tensor.
Why are we saying
On 3 dimensions.
Why on 3?
Because I'm taking the time out to show you. I'm taking it to show you. I want to take the time out to show you how the spatial, well, this is very important. At least if you want to know the curvature of the universe, if you're an astronomer, I'm talking from the point of view that we're going to try to connect this to actually observations and know what universe we're living in. So we need to understand this, you know. Right? Yes, there are time here, and it's very complicated. The whole shit is hideous. But I'm trying to, you know. I mean, this is not that hideous once you derive it, but to get from there to these things is, it's not incredible, but it will take a few pages of time. There's a nice calculation in Steven Weinberg's old book, I think it's the best, maybe, Gravitational Cosmology from 1972. He derives this from the equations of Einstein equation. I think it's fairly lucid. There's another one in lecture notes by Daniel Bowman. Yeah, another. So it's not incredible, yeah. It would take like a whole lecture or two. And I'm not a very big specialist on this stuff, so it's not my, I don't want to do it. God is not looking at it. Okay. So he doesn't want to do it. Okay. So you can do it with the GR tensor with Walid. Okay, so how do we get observationally this curvature? Not so bad. Immediately we have only 2 parameters, really. In the Newtonian naive thing, the very naive Newtonian, very basic stuff. We said we had 2 parameters, the scale-free density and the scale-free constant. You see why the constant is important? It's important. Okay. So you had 2 parameters. You want to connect these 2 parameters. Observation. So how do you do this? Okay. So how do you do this? Here are Newtonian parameters turned relativistic. The 2 parameters, the density and our constant divided by a squared. Yeah. The constant divided by a squared and the density multiplied by a by g or okay. So we define something called a critical density. What is the critical density? It's a density when the curvature is 0. So put here k equals 0, flat universe. This will be its density. This is called the Hubble parameter, a dot over a whole squared. We call it the Hubble parameter. Okay. It's a logarithmic rate of expansion, like we explained before. So this is our our critical density. If you are more dense than this, the universe is a 3-sphere. That's why we call it omega naught greater than 1. For example, omega naught is the critical density measured today. Local universe, not like before. Less than 1, it's hyperbolic. 1 is flat. So our 3 cases then are connected in the density because we only had 2 scales on the problem. The homogeneous density and this constant of integration that turned out to be a curvature. Okay? So we can define an omega, which is the ratio of the actual density to this critical density. And this is this. This is a very important cosmological parameter. The ratio of the density that we try to measure in the universe and the critical density that makes it critical, meaning this. Now, and there is an important property. Since all these things are positive, a squared, c squared, and a squared are positive, if you start with a sphere, a 3-sphere, you always remain positively curved. This cannot change sign, cannot become negative if you start with positive. And if you start with 0, it will always remain 0. If you start with negative, meaning this thing is negative here, minus 1 over r squared or minus 1 in the other convention, then this will remain always negative. So you cannot change from positive curve to negative. But through things like inflation, you could maybe start with positive and inflate it to be almost indistinguishable from flat. Because you inflated it so much that the radius of curvature became almost infinite. Very long. So, but that's another story. Okay, so people in my time, when I started doing this 30 years ago, or at least started learning about it 30 years ago, people tried to measure this thing directly from observation. They went and 30 years, in fact, earlier than 30 years, but I started 30 years, in fact, since they were trying to measure this since the 1960s or 70s, something like that. What is the, are we living in a curved positive, curved negative, or flat, or what is it exactly? So they were trying, people like Sandage and Zwicky, I think, were arguing about the Hubble parameter, how much it is. So what is the local Hubble parameter? How do we measure that? We'll get a bit more detail tomorrow, but here is more or less how you can do it, how you interpret it naively as a speed of recession. If the universe is expanding, galaxies are moving far away from us, and locally the expansion can appear like a speed. Okay, we'll take it naively. It's not how it is really, but naively we'll consider it, because that's how people like Hubble consider a speed. They measured redshift, meaning a line being redshifted, the same element, we see the same lines here, and translated into frequency, angstroms. Instead of being 6,000, they became 8,000. So 6,000 is like green or something, I think. 8,000 is red. So it's redshift, the same spectrum. So people can know. And redshift means the wavelength is expanded. So it means things are moving away from us. Wow, up to 1,000, train moving in the station, changing. Okay? And you can measure then distance against velocity, and this is your Hubble parameter. How we measure distances and velocities exactly, we'll get to it tomorrow. But I wanted to just mention here, how do we do that? This is not always trivial, at least once you go beyond on cosmological scale. This is not very far, this is cosmological. This is 500 megaparsecs or so, but once you go to larger distance, gigaparsecs, and so it doesn't work this way. So, but anyway, you can try to measure the density now of the universe and your Hubble parameter from something like that, and measure omega. Look, is it greater than 1? Are we in a curved universe? Is it smaller than 1? Are we in a hyperbolic universe? Is it 0? Are we in a flat? So this is the questions you want to answer, cosmologically speaking. You know, for people working in physical cosmology. What kind of universe we're living in. So people try doing this. And then it may appear trivial. Maybe there's nothing so deep about this. No, there is. Because it turned out, people were, until 1995 or 98 or something, people were really trying to measure omega naught. And the people doing inflation, which Alexei will talk about, they wanted omega naught to be zero, because if you inflated the universe really hard, then omega naught will be close to zero, you know, because you expanded it into a flat space, you know. But they measured omega naught to be 0.3, meaning we are in a flat hyperbolic universe. Sorry, not in a flat, but in a hyperbolic universe. And they kept on looking. Maybe there's more dark matter. Maybe how did they measure rho naught? They measured it from movements of things in the sky and made budgets and added it up and so on.
It was a positive 0.3?
No, it is omega 0.3, meaning the curvature is negative. Meaning curvature is negative. Omega is like -1. So this makes it negative, at least in this context. Okay, so people thought that they don't want a negative universe, but that's what it said. And then it turned out they can't measure the 70% of the density like that at all by seeing things move and making budgets of galaxies and dark matter and so on. There's something completely exotic that is not there. You can't measure it by just looking at the dynamics of galaxies and how things move and making budgets. It doesn't work. There was a Rambo. There's something else in this budget. There's something new. There's something additional here. So you can, by doing these things, as like in Tycho Brahe and Kepler, and the 1 arc second or whatever, or I don't remember what the error was, a small error, minutes maybe, in degrees of the orbits of some planet, and you find something really new. There's something really fundamental missing here. Okay? Very quickly, I don't know how far I'll go with this, but yeah, maybe I'll go another 5 minutes, Alan?
Yes.
Okay, I'll go another 5 minutes. Okay, so you can't do it this way, okay? So how do we do it nowadays? I won't go into the whole history because I don't even remember. It's because I went into galaxy dynamics in a minute. I don't, you know, so I don't remember what was happening in detail. But we need to solve this equation. To solve this equation precisely, we need rho as a function of A. We said that rho for matter is 1 over a cube, 1 over a to the 4 for radiation because it's redshifted, and constant if you have a cosmological constant. So this dark, strange thing. Now this is not so exotic, by the way. You can have a bunch of springs with a potential energy, with an energy density that is constant as the density change, the mass density changes and the potential changes. You can do that, but it's strange for a cosmological thing. Where are the springs? where is the springs? Okay. So you can do it like that, and you can do it more formally through the first law of thermodynamics, or the divergence of the energy momentum tensor and so on. You do an equation of state. You have an equation of state that you all know probably, or at least most of you, like for an ideal gas, P equals rho T over mu. Ideal gas, PV equals nRT. Identity. Okay, PV equals, this is another equation of state. P equals dc, relativistic. So you can apply the second and the first law and put the strings, and you get that that A changes like that. So if P, there's no pressure, if this is 0, then P rho goes 1 over a cubed, like normal matter, like the Newtonian stuff we started with. If this is a third, like for radiation, this is 1 over a to the 4. And if this is -1, a negative pressure, this gives you the dark energy cosmological constant equation state. Dark energy in the form of constant vacuum energy. And this is how they go. That's why we think the universe was radiation dominated in the beginning, and then because this is a log-log plot, of course, and so this is the matter. It wins out in intermediate state, and the radiation wins out before, because in earlier times, because it's 8 to the 4. Within an ingredient, this is really coming. Doesn't change, so it's very small in the beginning, but wins out in the end. Okay, so this model is these components, and that is called the lambda CDM model. This is lambda, and this is the CDM. Radiation, because it doesn't affect too much nowadays, is gone. It should be, I guess, called the photon lambda CDM, gamma lambda CDM, because there's radiation in it too. And neutrinos, so mu, gamma, lambda CDM, not bad. All right. Right. So for a flat universe, you can solve this very easily, and you can get a rho to the t to the half or t to the 2/3, and then for the dark energy, you get these limits. Only radiation. You can put them all together. Again, we can put the radiation and matter and lambda all together, but we're just doing simplified here to show you how they behave when one is dominant. So radiation only, t to the half, matter only, t to the 2/3. That is how A varies with time. We're solving the Friedmann equation for zero curvature. Okay? So we're taking this is very easy to solve for zero curvature. And inflation, e to the h, which is constant, t, exponential expansion. So these are the three. And you'll see for normal matter, because these go to the A3, A to the 4, and the curvature term goes to like k, a to the -2. At very early universe, these are always more dominant than that. So for an early universe, it's always nearly flat. And this brings you to stories of why is the universe was nearly flat and remains so, because if you change omega too much, the universe would either expand very rapidly, or it will recollapse very rapidly. So omega is really fine-tuned. So why is omega really fine-tuned? And why is lambda? If lambda is big, the universe will just inflate from the beginning, and you wouldn't have galaxies or planets or stars or planets or people or anything. Right? So there's a fine-tuning there. Maybe Alexei will speak about it. People think it's connected to inflation. Okay, I'll stop here. I'll just mention one thing, that we cannot, this is all very nice, but we cannot measure A of t directly. What we see is things, objects, galaxies, stars, supernova, and so on, and we can make distance measures to that. So we need to get distance measures from our metric to compare with observation. We cannot this is all very nice to solve these things, but we need to try to see whether omega equals 1, omega, the curvature is positive, there is dark energy or there isn't, or what is, we need to know distance. We can't measure the stuff. We don't know A of t. How do we measure A of t? Okay, so what do we measure? We speak tomorrow about what we measure. Okay. Yes?
هو هنا في those 4 points ده كده ترتيب chronological اللي حصل ان هو في الاول inflation.
Yeah, actually by chance, maybe, I don't know.
So we يعني هو حضرتك هنا بتimply انه at first there was some vacuum domination, مع ان ده ما كانش باين في الجراف ان كان في vacuum domination.
No, I don't have that here. No, it's not here. But
the previous graph كان
Did it
radiation كان
No, it
radiation
didn't.
هو اللي بيدومينيت وبعد كده
radiation and then matter and
وبعد
then
كده-
vacuum. No, I don't have the inflation here.
بس
There could be, or there probably was, yes. So, the standard picture,
نأسيوم ان هو وقت الانفليشن كان في vacuum domination.
because that's how you get inflation from. That's how you get inflation, because inflation is this. So to get inflation, you need vacuum domination. You need exponential solution to the Friedmann equation. So that's why. Yes. So we're having another inflation now, but of very low energy. Okay, for some reason that nobody knows. So it turned out that to be our naive thing is quite deep. Yes, we are having a second inflation. Nobody knows why there was a first one or a second one, but we know that at least the second one is there, almost certainly.
Okay.
Is it inflation really? A de Sitter space?
بس هو مش هيبقى exponential this way يعني.
Nowadays, not yet.
Okay.
If it continues, it will be this way.
Uh-huh.
Nowadays, not yet. It's only 70%, and only very recently. But if it continues, it will be like that. If lambda CDM is the absolute model, the matter will keep on going down, the radiation going down, and you'll have complete. And you will have inflation, yes, on a very low energy, but inflation nevertheless. And then you'll have, next time we'll speak about cosmological horizons, you'll have a de Sitter horizon and so. And all the galaxies will go far and you will only see Andromeda. Well, and maybe some others. Only the locally bound galaxies you'll be able to see. The others will inflate away. Most of the others, there will be a horizon, a de Sitter, like an inflation, connected to H, which is connected to the cosmological constant. So some galaxies will still be there, but a lot of it will inflate away. Okay, any questions? No questions? Hello? Okay. Okay, so basically next time we'll speak about things like conformal time and co-moving distance and try to get these distances. How do we, get distances from a theory and connected, this is how you get your distance, and here it's not, it looks scary, but it's not really difficult. Okay, so this is how you get your distance, and then you compare it with things like luminosity, how bright things are in the universe, or how big or small angular distances and so on. Try to calibrate our model and find whether it is how much matter, how much. In this way, you don't get how much radiation. You get it from cosmic microwave background, but you can get how much matter, how much lambda, and how much curvature. So it turns out that we can do it. Okay, so we do that next time. At this time, we close at this time. These are the different behaviors of components of the lambda CDM model. Okay? Okay, so I guess that's it.